We are back once again. This is the daily LeetCode grind, day 44. We have some good news. We fried the smallest strings with swaps problem. Also, shout out the Copy Ninja and I'm Just That Guy. He commented W moment, W human, W experience, W planet. Also, W Copy Ninja moment. We have some problems due as always, and we did the smallest string with swaps, so that went well. I'm also noticing that there needs to be a rest period between sessions. The optimal session was 90 minutes, and I think that was going well. The focus locked in. Once you do 90 minutes, you're done. And it was about the quality. Now I'm going for quantity, and I think it's actually having an adverse effect. So I think it would have been better if we just worked at the original pace. So I think that's what I'm going to try to do. That being said, we're still working through the Explore card, maybe Evaluate Division, which I'm fairly certain we will not solve. We also have Optimize Water Distribution, Village, I'm fairly certain we will also not solve. And if I can find the Explore card here for graphs, I think what we're going to actually try today is find if path exists in graph. We're going to try and find if path exists in graph, and just keep going. Actually, we might just keep trying at, honestly, we might just keep trying at the disjoint, the problem earlier with, evaluate division. That way we just work sequentially through the problems. I think there's, now I'm realizing I think there's no rushing this. I think you can only go at the speed at which you're learning, and I think being blocked by problems is good, so you just gotta slowly work through the problems and make sense of them. That being said, this problem makes no sense, and it's also probably impossible. So I'm gonna try it again today for an hour. I don't think it's likely that we'll come up with a solution, but we know that we can use union or disjoint sets somehow, so I think we should keep working at it, and hopefully we can find a secret cheat code or secret way through. But yeah. Also thinking about doing a regular stream instead. Maybe we'll do something like we'll do the hour at 7 p.m. or 8 p.m. I think that could be cool. All kind of grind at the same time. That'd be kind of hype. But that being said, I think that's what we might try and do. And yeah, we'll do 399 evaluate division to start, and we'll have an hour to try it. So let's just jump right into it. Also, make sure to join the hyperbolic coding chamber. Thousands upon thousands of people joining every day. Yeah, and I feel like, I'm also pretty dead. I think you can tell. Too much grind. I think the grind now is becoming getting a bit sloppy with the grind. I think and it's not even a grind. It is what it is. You learn at the speed you learn at. I think just going too fast, take it slower, learn what you can, and then that's all you really can do. And I think struggle is a good elaborative encoder. So the more you struggle on a problem, I feel like the more you actually learn from it. And so we're also, in doing a problem like this, we're struggling and trying to figure out different ways to visualize a problem, which is also always good. And so I think we just need to take our time with it, and we'll get where we need to be going. That being said, should we do evaluate division? Well, I feel it's a good problem. I think we should continue with breadth at least and see what we can do with, where is the Explore card? Let me load it up. So we're back. We have find if path exists in graph, and then paths from source to target, and then we'll do clone graph, and clone graph is bullying me as a problem, so let's just jump into it. Let's going to do find if path exists in graph. So there's a bidirectional graph with n vertices, where each vertex, so we have a bidirectional graph with n vertices, where each vertex is labeled from 0 to n-1 inclusive. to a bidirectional graph with n vertices, where each vertex is labeled from 0 to n minus 1 inclusive. Which makes sense. Edges in the graph are represented. Edges in the graph are represented as a 2D integer array edges, which makes sense, where each edge sub I is equal to u sub I, comma v sub I denotes a bidirectional edge between vertex ui and vertex vi. Every vertex pair is connected by at most one edge. So every vertex pair is connected by at most one edge, and no vertex has an edge to itself. This is pretty cool. You want to determine if there is a valid path that exists from source to vertex destination, given edges and the integers n, which is basically all the vertices, edges, source, destination. Return true if there is a valid path from source to destination, or false otherwise. So I think you could do this with a depth first search. And we see here that n is equal to 3, so we have 3 nodes, 0, 1, 2, and the edges that we have are 0, 1, 1, 2, and 2, 1. And our source is going to be 0. Our destination is 2, and we want to know if we can get to 2. And there are 2 paths from vertex 0 to vertex 2, 0, 1, 2, and 0, 2. Now we have n equals 6 and edges 0, 1, 0, 2, 3, 5, 5, 4, 4, 3, which actually creates 2 separate graphs because they're not connected. Output is false. So I'm thinking, what are some things we can check? We want to know for certain that source and destination exist within the graphs or multiple graphs, right? We want to know that edges at least has 2 elements every time, which it does. And we know that, oh, it looks like edges can be empty. There are no duplicate edges, there are no self edges. And we know that source is always less than destination. And so our input is basically always valid. And we know that source, or UI, is less than VI, and UI never equals VI. So this is interesting. So if we want to find if path exists in a graph, we could do a depth first search, right? But if we're doing a depth first search, right, we want to know if a path exists. So if we can ever run into our node, right, and it will equal destination, then we'll know that we'd be in business. So I think what we can do is try and visit every node, every neighbor of a particular node, right? And the only way we can do that, I think, to start, is I think we would need to transfer, or we would need to convert edges to an adjacency list. But now I'm thinking maybe we could skip that step. If we have edges between 0 and 1, no, I think we'd actually need that step because we need to know what neighbors we can get to starting from a particular node. So the goal would be to create an adjacency list where we have 0 and it's connected to 1 and 2. And we have 1 which is connected to both 0, 1 which is connected to both 0 and 2, and then we'd have 2 which is connected to both 0 and 1. So the goal is to create this adjacency list. And so if that's the case, I think we can do that. So I think the best that we could go for would actually be a function which would convert the edges to an adjacency list. And then once we have the adjacency list, we can traverse adjacency list and search for destination. So let's create that function that will create the adjacency list. And so we're actually going to modify this adjacency list by reference. We create a map of number to number array, and then we'll have a DFS which will take in our adjacency list, which is empty. Wait a second. Oh, right. So we actually don't need a depth first search to create this adjacency list. I think we could just iterate through edges. So we can say for const edge of edges. And we could even the structure, we could say vertice 1 and vertice 2 of edges, right, and create this adjacency list. So what we could say is if adjacency list dot has vertex 1, right, what we'd like to do is, if it has the vertex, right, what we'd like to do is do adjacency list dot get the array for this vertex, right, and push onto it v2 as a vertice. Otherwise, we'd like to do adjacency list dot set v1, right, to an array that would have v2 in it. Right, and I think we're going to want to do this for v2 as well because we want to know the connections. And I think what we could do is just create an array of tuples where we have v1 and v2, right, and as well v2 and v1. And we can just do this for each. We'll say v, and it's a little confusing, but we'll say vertex 1, vertex 2, and so we can just use this singular if for both of them. So if adjacency list has vertex 1, right, then we want to get vertex 1 and push vertex 2 onto it. Otherwise, you'd like to set vertex 1 to an array that just has vertex 2 in it, and by swapping the tuples in the next index, we can do the same for the opposite. So we can check, right, that our adjacency list is being created, and we'll just return true to start and see what our adjacency list is looking like. So we're saying if the adjacent list has vertex 1, so we're saying argument of type number is not assignable to parameter of type number. So I think vertex 1, oh, and I have right. So we want is to actually destructure this like so, and then I think we will have what we're looking for. So our adjacency list looks like 0, 1, 2, 1, 0, 2, and 2, 1, 0. So that actually does look good, and we'll try it for just one more test case. Actually, it's a bit convoluted to set that test case up, so we'll see that our adjacency list makes sense for now. Now we want to traverse the adjacency list and search for destination. Right, so this is where we could actually, and maybe, so we have this adjacency list, and we want to know if there's a path that exists, right, to a particular destination. So if that's the case, I think what we could do, since it's undirected, we could start at a particular node, right, like 0, right? If we haven't seen it before, we'll add it right to our visited set, and then we're going to want to visit 1. Now when we visit 1, we're going to want to prevent simple cycles, so we'll remove 0 from that adjacency list. When we visit 2, we'll do the same, right? But we'll just keep iterating, right, until vertex, so we can just iterate through our adjacency list kind of sequentially. And so we'll just say for const root or node, right, and neighbors of adjacency list, right, we're going to have a visited set. It's going to be a set of type number. And what we're going to do is we're going to say if node, right, if visited, right, doesn't have a reference to this node, right, we're going to say node, but it's really just a number, right? So if it doesn't have the node, right, then we want to add it. We'll do visited.add node, right? But additionally, what we want to check is if node equals destination, then we're actually going to return true. We're actually going to return true. And so that would mean that we found it, and at the end, right, that would mean that we have false. We actually still need to visit our neighbors. And so our cases here are the code we write here, adding the node and checking if it's equal to the destination. We're actually going to want to run that for pretty much the node and its neighbors. But I think we're going to have to duplicate just a little bit, because we're going to have neighbors dot for each, right? And we also don't want to forget our step to remove the simple cycles, right? So we're going to have n, right, for neighbor. And we're going to say if we haven't visited this node before, right? If we haven't visited this node before, right, then we're going to add it, right? And if it's equal to our destination, right, that's actually a good thing. We'll return true. But additionally, right, we want to remove simple cycles. So we'll say if adjacency list dot has, right, this node, right, let's say we're at 1, right, which would have this node, right? So it does have this node. So what it means is we're going to be able to get that array of values. We'd say adjacency list dot get n, right? And we want to basically do adjacency list dot set n, right? And we want to filter out the current node value. So we'll say adjacency list dot get n dot filter v, and we'll keep all values that do not equal the node's value. And so we'll end up filtering out 1 and I'll end up filtering out 0 for both nodes 1 and 2, which is good. And then we'll visit but it's possible that node 2 has more connections, and so yeah, this is very, very convoluted. I think we might want to just, while I know this version works because we've used it for a different problem, I think we just would like to use a depth first search. So what if we do a DFS with our adjacency list with visited and source, which would be our source, and we'll pass in destination, which will be our next destination index, right? What we're going to want to do is return this DFS because it's going to check whether or not a path exists for this node. So for that DFS, we'll have a function DFS adjacency list, right? It's going to be a map of type number to an array of numbers. Then we're going to have visited, which is a set type number, as well as source, or I guess we'll say cur, which will be a number, and destination, which is a number but is ultimately our goal, right? And so the first thing we want to do is say if cur equal destination, right? Then that's a great thing. We want to return true, a path exists for it, right? Otherwise, right, we want to be at a node or want to visit. If we visit node 0, we want to visit our neighbors 1 and 2, right? And so if that's the case, right? So it ends up looking a lot like the code we were writing in the while loop, but I think it'll be more intuitive in here. So we'll say if visited, right, does not have, so I think we're jumping too far ahead. Let's just say we're at node 0. Now we want to check, we haven't seen this node before, so we'll add it to visited. Then we want to visit our neighbors, which is 1 and 2. We visit 1, it's not equal to destination, but we want to visit our neighbors, but we already visited 0, so we don't want to visit 2. So we still want to remove simple cycles as well. Like we said, if visited does not have cur, then it will add cur. Right, so we'll add 1, right, and now you want to visit node, this node's neighbors, and to get those neighbors, we'll say neighbors equals map dot get cur, which would give us the array. We'll say neighbors. We'll say for const n of neighbors, right? And we're going to say if for const n of neighbors, right? Before we go into the neighbor, we want to remove the simple cycle for the neighbor, right? And so to remove the simple cycle, right, we'll say if adjacency list dot has n, it means it has an array for it. And so like we said, we'll do the adjacency list dot set n, right? But the value dot get for n and filter the values to all values that do not equal cur, right? To filter out those simple cycles, which actually be linear time, and it's definitely not a goal here. If adjacency list has n, we'd filter out those simple cycles, and then we want to actually run depth first search. We'll say if depth first search with the adjacency list with visited, right, with n, right, and with destination staying the same. If that's true, we return true, right? And so we remove the simple cycles up here. Otherwise, we return false, right? Because we would have propagated all the way downwards and we wouldn't have anything to show for it. We use map, and we mean adjacency. So the first case returns true, and let's see if this makes sense. So our process exited. So it looks like maybe it took too long. And remove more simple cycles. So we would have, my brain is fried. My brain is actually fried. I literally can't think. The code that I'm writing doesn't quite make much sense. I think we just did too much prep today. Too much problems, not enough breaks. The code that I'm writing, I'm writing it and I notice that it's not exactly clear. So let's make this make sense. Bidirectional graph with n vertices where each vertex is labeled from 0 to n-1. Edges in the graph presented by, we have a DFS, you convert edges to an adjacency list. Not visited has cur, visited.add cur. Const neighbors equal adj.get cur. Const n of neighbors, adj.has n, adj.set n, adj.get n. We'll set n equal to this filtered array. All the values do not equal to cur. Then we end up visiting n. So it actually looks like we're not. I think we are only interested in doing any of this if visited has never seen n before. So we get further, but in this case, we're just going too deeply. So the method by which we are visiting the graph is very, very convoluted. We're doing filters, we're going deeper, we have a for loop. We want to find if a value exists for a particular path. We have the adjacency list. The way we go through the adjacency list is strange. We're starting at the main node we haven't visited before, so we add it. Then we want to visit our neighbors. We fix the simple cycles. and we visit our neighbors, we still end up going too far. So I think the code does work, and this would work as a solution, but it's really sort of like a brute force solution. We run it for this value. Let's see what we get. Right, so it does work. It's just a little bit out there in terms of speed. So if we created a smaller graph, we'd have our adjacency list 0 maps to 0 and 1, move the simple cycles, then we'd visit 2. We haven't seen 2 before, so we'd visit 1, we'd filter 2 out, and so that is interesting. How could we go faster? Const n of neighbors if not visited. Adjacency list has the node, then we set n equal to get and filter v. V does not equal cur. And we're still looking for a destination throughout it the whole time. Maybe if we did this iteratively, it would make more sense. Yeah, I think we need more. I think I usually never stop the session this early, but I think we just need more rest. I think there's way too much prep. I think I've done, or made way too much problems done. I think I've done like 6, finished work at like 5 or 6, and then we did like 6 hours. So 8 hours of work and then 6 hours of problems is just, I think, a little too much. So much so that I'm thinking about, I'm looking at the screen, I'm seeing the code that I'm writing, but it just doesn't quite make sense. So we're getting sloppy in the problem. So I'm thinking we should just reduce the total number of hours. Yeah, 8 hours of work and then 5 to 6 hours of problems. It's just too much, I think, depending on the day. So what I'm thinking is, I think we're going to stop here and then reevaluate how we do the prep. I think after work we do an hour and a half, maybe take a break, and then do another hour and a half, then take a break, and then maybe do another hour and a half, rather than finish work, do 6 hours straight. So I think that makes sense. But yeah, I'm sure if we come back to this problem tomorrow, which we will, to make it will, I feel like I know how to get the solution, but my brain just isn't working. So I think we'll stop there.